All right, I've got Theorem 3 up here on the board. This is Theorem 3 from 16.3 in your text, okay? And there are a couple of vocabulary words in here, so I've just sort of underlined them and then defined the vocabulary down here, okay? So this says the line integral of a vector field f along a curve C is going to be independent of path. Now, path is a word that I'm going to define in just a moment, but basically what we just saw with the fundamental theorem was saying that vector fields were conservative vector fields, the work integrals was going to be independent of path, meaning that if you integrated a conservative vector field along a piecewise smooth curve from A to B, you were going to get the same result regardless of which curve you took to get from A to B. You were just going to get the potential function at your ending point minus the potential function at your starting point. Okay, I've got path underlined here. Path means a piecewise smooth curve. Okay, so I'm not talking about just any old curve that takes me from A to B. It does need to be piecewise smooth, and we'll use the word path to mean that. Okay, so we're going to have a vector field that's independent of path on a region D. Now, that's important just because I might have some vector fields that have a restricted domain. So this is only going to apply where they're defined, or where they're continuous, or where these hypotheses are satisfied. Okay. Often that region might be all of 2 space, or for a vector field in 3 space, all of 3 space, but it's okay if that's some subset of 2 space or 3 space. Okay. All right. If with 2 F's just means if and only if. So this is a two-way implication. Okay. And it's if and only if. This is sort of a new symbol where we've got this loop on the integral sign. It's not necessary to write that, but it's kind of nice. We're talking about here the integral along a closed curve C. So this is saying the work integral that we get is going to be 0 for every closed path C in D. So I've already said path means that it's a piecewise smooth curve. Closed simply means that the starting point is equal to the ending point. So if I were to parameterize it as r of t with a less than or equal to t less than or equal to b, that would just mean that r of a was equal to r of b. So a circle is an example of a closed path, okay, where I start and end at the same point. I could have something like this, where that's my starting and ending point, that's my closed path that comes back to that same point. I could have something that does this. Maybe this is my starting and ending point, and it loops around, but then it comes back to that same starting point. All of these would be examples of closed paths. Okay. All right, so let's go ahead and prove this. Now this is a two-way implication. So it says if it's independent of path, then the integral along a closed curve will be 0. And it also says if an integral along a closed curve is equal to 0, then it's independent of path. I'm going to just prove one direction. Okay. So let's suppose the work integral for a vector field f is independent of path. Okay, and let's choose C now to be some closed curve. Okay, so I'm going to let this point be point A. Okay, so I've got that, and I'm going to just choose another point somewhere along here that I'm going to call B. Okay, and then I can break this curve up so that I can say, here's C1. C1 takes me from A to B, and here's C2. C2 takes me from B to A. So I'm going to say C is just C1 plus C2. So C takes me from A all the way around to A. That's just following C1 to B and then following C2 back to A. Okay. So I can say that the integral along C of f dotted with t ds, and because C here is a closed curve, if I want to, I can put that little loop on the integral sign to indicate that. Okay, well, this is just the integral along C1 of f dotted with t ds, plus the integral along C2 of f dotted with t ds. Okay. But notice C1 goes from A to B. C2 goes from B to A. I know another path that goes from B to A, negative C1. C1 with its orientation reversed would also go from B to A. So I can say this is the integral along C1 of f dotted with t ds plus the integral along negative C1 of f dotted with t ds. Because we've got a vector field where the line integrals of that vector field are independent of path, and because these two paths have the same starting and ending point, they start at B, they end at A, this integral I know is the same as this integral. But if you remember when we talked about the orientation of curves for line integrals, we said for a work integral, if you reverse the orientation, it just gives you the opposite of if you, so this is a C1, it gives you the opposite of if you'd integrated along the original curve with the original orientation. So this would be the integral along C1 of f dotted with t ds minus the integral along C1 of f dotted with t ds, and that would be 0. Okay, so what we've proved is one direction, that if you've got something that's independent of path, then the line integral around any closed curve will be 0. Okay, proving it the other way is basically making the same argument in the reverse direction. If I know that this is 0, then I can say, okay, if I know that for any closed curve it's 0, I can say, okay, so here's A and here's B. Let me just draw two curves that go from A to B. So there's curve 1 and there's curve 2. Now I want to show that the line integral along this path is the same as the line integral along this path. Well, I know that the line integral along this path plus the opposite of this path would create a closed curve, and so I know that that would be 0. So that means I know that the line integral along here plus the opposite of the line integral along here is 0, so those two line integrals would have to be the same. Okay, so I sort of talked through that one instead of formally writing it up. Notice a consequence of this is because we know that conservative vector fields are independent of path. If I have a closed curve, the line integral of a conservative vector field around a closed curve is going to be 0. The work done by a conservative vector field around a closed loop that returns to its starting point will always be 0. Now, I phrased this as a theorem about line integrals that were independent of path. That's what your book does. Then they move on to Theorem 4, where essentially they're going to say the only vector fields where we're going to get independence of path are conservative vector fields. So that we really could have phrased this as a theorem about conservative vector fields. Okay. Now, they are going to, just because they're proving this in the textbook, they are going to add a couple of conditions to the region D. Okay. So let D be an open region, and it's also a connected region. So let me just remind you what those things mean. If I have an open region, so for example, I could have an open disk. So that would be all of these points inside the circle, but not including that boundary. The significance of a region being open is that if I'm at some point in the region, I can go a little way away from that point in any direction, and I'm still in the region. Okay. If I had a closed disk that included the boundary, I lose that property, because if I'm on the boundary, it's possible to go a little way away in certain directions and I've left the region. So the significance of an open region is that if something is true on an open region, it's true at every point in that region and a little ways away from those points in any direction. So you can go a little ways away and you don't lose any of the niceness conditions that you have. Often we'll have niceness conditions like that our functions have continuous components or continuous partial derivatives or something like that. Okay. Connected simply means that it comes in one piece. And I think the simplest way to illustrate connected is to actually illustrate what is not connected. So this is not a connected region. This is a connected region. Okay. Not connected, it comes in more than one point. Now, I will point out this, as long as there's a point right here where the two little parts meet, this is connected because those two parts are touching. Okay. So connected basically means it comes in one part, okay? But we can more formally define this, okay, for any 2 points in the region. There is a curve in that region connecting the points. So here, if I had a point over here and a point over here, I can draw a curve that connects those points. It would have to pass through that point, but I can do that. Okay. Over here, if I had a point here and a point here, any curve that's going to connect those points is going to have to leave the region. Okay. All right. So this was illustrating connected. I will just point out the regions that I drew that were connected, I didn't draw open regions because I did include the boundaries. I drew those as solid lines. So for us, we're going to be working in open and connected regions. I was just here illustrating what it means to be connected. Okay. All right. And what Theorem 4 says is basically what I said a moment ago, that if you've got a vector field where you get independence of path, it's conservative. So if the integral along C of f dotted with t ds is independent of path, in an open, connected region D, then f is conservative. Okay. What that means is that there is a potential function. So there is a potential function f such that my vector field f is just the gradient field for that real valued function f. Okay. Now, this is proved in your textbook. I'm not planning to prove it in these lecture videos. If you're interested in the proof, I'd encourage you to read through it, and I'm certainly more than happy to talk about it with folks in office hours and answer questions about it. Unfortunately, I don't think it's one of those proofs where it really helps you to understand what the theorem is saying. It does demonstrate why it's true, but I don't think it's one of those things that really helps our understanding of, hey, these two things are equivalent. If you're independent of path, you're conservative. Okay. And so just in the interests of time, and because this isn't a class where the focus is on proof writing, I'm not going to do the proof in class, but I am very happy to answer questions about it in office hours. You are responsible for knowing the theorem. You are not responsible for its proof.